The Milky Way is dying. Not eventually. Now. Slowly, yes. On timescales that make human history look like a camera flash. But the process is already underway, has been for billions of years, and the numbers are not subtle. Stars are dying faster than new ones are being born. The galaxy is running out of the raw material it needs to make new suns. And the stars you see tonight, the ones people write poetry about, the ones sailors navigated by, the ones every civilization in human history looked up at and felt something, most of them are so far away that you're seeing light that left before your species existed. Not before your country, before your species, before Homo sapiens walked upright on this planet. You are looking at history and calling it the present. That's the first thing we need to fix. Because once you actually understand the scale of what you're looking at, the distances, the timescales, the death toll already accumulated in that band of light across the night sky, you cannot go back to thinking about the cosmos the way you did before. And I think that's worth an hour of your time. Let's start with light. You have to. You genuinely cannot understand anything else about this topic without first wrestling with what light speed actually means. Not as a number you've heard before, but as something that rewires how you look at the sky. Light travels at 299,792, 458 meters per second. That's in a vacuum. That's the measured number, not an approximation. It's so precisely measured that in 1983, scientists redefined the meter itself in terms of it. And at that speed, faster than anything else in the universe, as far as we can tell, it still takes 8 minutes to reach us from the sun. 8 minutes, our nearest star. If the sun vanished right now completely and instantly, we wouldn't know for 8 minutes. We'd be sitting here, going about our morning, and then the light would stop arriving and we'd figure it out pretty quickly after that. But the point is, what you see when you look at the sun is not the sun as it is. It's the sun as it was 8 minutes ago. Now push that outward. The next nearest star to us, Proxima Centauri, is 424 light-years away. That means the light hitting your eye from Proxima Centauri tonight left its surface 424 years ago. Whatever that star is doing right now, tonight, in this actual moment, you won't find out for another 4 years. That's the nearest star. The nearest one. The Milky Way is roughly 100,000 light-years across. Stars near the galactic center are about 26,000 light-years away from us. The light you're seeing from those stars left when Homo sapiens was still painting caves, before any written language existed on this planet, before any city was built anywhere on Earth. You look up at the center of our own galaxy and you are watching something that happened before recorded human history began. Not ancient history, prehistory, and some stars in the outer disk, up to 100,000 light-years away. The light leaving those stars right now will arrive at Earth long after our sun has burned out. We will never receive it. It won't get here in time. This is what people miss when they look at the night sky as if it's a live view. It isn't. There is no such thing as the sky right now, not for anything beyond our immediate neighborhood. The night sky is a composite of historical records, each arriving from a different distance, each carrying news from a different moment in the past. When you look up all at once, you're seeing photons from objects separated by thousands of years of history, all hitting your eye simultaneously. It's like reading a newspaper where every article was written in a different decade and nobody told you which one. Now, to understand why the Milky Way is a graveyard, you need to understand what a star actually is. Not what it looks like, but how it works. Because the mechanism of stellar death follows directly from the mechanism of stellar life. A star is a gravitational collapse that can't finish. That's the operational description. You take an enormous cloud of hydrogen gas, masses ranging from about 1/10 to 100 times the mass of our sun, which is itself 333,000 times the mass of the Earth, and gravity starts pulling it inward. As the cloud collapses, it compresses. Compression means heat. The core temperature rises. At around 10 million degrees Kelvin, something happens. Hydrogen nuclei, which are just protons, start moving fast enough that when they collide, they don't bounce off. They stick, they fuse. Through a sequence of steps, 4 hydrogen nuclei become 1 helium nucleus. And in that process, a small amount of mass disappears. It converts directly into energy. The mass that vanishes gets multiplied by the speed of light squared, which is approximately 90 quadrillion meters squared per second squared, and even a tiny bit of vanished mass produces an enormous amount of energy. That energy pushes outward, and it balances almost exactly the gravity pulling inward. That's a star, a sustained standoff between fusion pushing out and gravity pulling in. For billions of years, this standoff holds. Our sun has maintained it for about 4.6 billion years. It will maintain it for roughly another 5 billion. But the star is spending its fuel. Hydrogen in the core converts to helium. Steadily, over billions of years, the hydrogen runs low. And when it runs out, the standoff ends. Gravity wins. What happens next depends entirely on how massive the star is, and this is where the graveyard gets populated. For a star like our sun, the end goes like this. As hydrogen in the core depletes, the core contracts and heats further. This extra heat causes the outer layers to expand enormously. The sun will swell into a red giant large enough to swallow Mercury and Venus, and possibly Earth. Then the outer layers drift away entirely, forming an expanding shell of glowing gas called a planetary nebula. Beautiful. Temporary. The core left behind, a ball of carbon and oxygen roughly the size of Earth, still hot, no longer fusing anything, is a white dwarf. It sits there, radiating stored heat into space, getting dimmer, getting cooler. Over hundreds of billions of years, it approaches absolute zero, what we'd call a black dwarf, a cold, dark, inert cinder. The universe is not yet old enough for any white dwarf to have completed this cooling, but they're on their way, every one of them. For massive stars, 8 times the mass of our sun or more, the ending is faster and more violent. These stars burn through hydrogen quickly, then fuse helium into carbon, carbon into oxygen, oxygen into neon, neon into silicon, until the core is iron. Iron is the endpoint. You cannot extract energy from fusing iron into heavier elements. In fact, it costs energy rather than releasing it. So when the iron core forms, fusion stops. The standoff ends not gradually, but in less than a second. The core collapses. Material that was spread over a volume the size of Earth compresses to a sphere about 20 kilometers across, at densities so extreme that a teaspoon of it would weigh roughly 1 billion tons. The infalling outer layers hit this suddenly rigid surface and rebound outward in an explosion, a supernova that briefly outshines the entire galaxy it lives in. Billions of stars outshone by one dying one. What's left is either a neutron star, the compressed core, spinning, radiating, or if the star was massive enough, a black hole, a region of space-time where gravity has become so extreme that the escape velocity exceeds the speed of light. Nothing gets out. Not light, not information, nothing. These are the bodies in the graveyard. White dwarfs, neutron stars, black holes, cold or dark or both. All of them were once stars, were once burning, were once possibly the centers of solar systems. Now they're just mass in the dark, and the dark is patient. Here is where the graveyard metaphor stops being poetic and starts being arithmetic. The Milky Way currently forms new stars at a rate of roughly 1 to 3 solar masses per year. That sounds like a functioning production line until you look at what the rate used to be. About 10 billion years ago, during the peak of star formation, our galaxy was assembling somewhere between 10 and 20 solar masses of new stars every year. We've already consumed most of the gaseous raw material. The interstellar medium, the gas and dust that lives between stars and eventually collapses into new ones, has been steadily depleted. Stars form from it, burn for millions or billions of years, and when they die, they return some of that material, but not all of it. Stellar remnants lock up mass permanently. Each generation of stars removes a fraction from the cycle that never comes back. Meanwhile, the dying continues without pause. Massive stars live fast. Some of the largest burn through their fuel in just a few million years before exploding as supernovae. Our galaxy produces on the order of 1 or 2 supernovae per century. That sounds infrequent, but the Milky Way is roughly 13.6 billion years old. At even 1 supernova per century, that's 136 million stellar explosions over the galaxy's lifetime, 136 million stars that no longer exist, each leaving behind a neutron star or a black hole. And that's not counting the far more numerous lower mass stars that quietly swell, shed their layers, and leave white dwarfs. That rate is much higher. The estimates for total stellar remnants in the Milky Way are frankly staggering. There may be on the order of 100 million neutron stars in our galaxy. roughly 10 million black holes formed from individual stellar collapses, not counting the supermassive black hole at the galactic center, which is in a different category entirely, roughly 4 million times the mass of our Sun. And white dwarfs, estimates suggest something like 10 billion of them. 10 billion cold, fading, slowly cooling objects that were once stars, against a total stellar population of somewhere between 100 and 400 billion. You're looking at a galaxy where the dead already number in the billions, and the ratio gets worse every century. Now combine this with the light delay problem we started with. This is where it gets uncomfortable. You can see roughly 9,000 stars with the naked eye on a clear night far from city lights. Most of them are within a few thousand light years, close by galactic standards. The most distant ones visible to the naked eye sit perhaps 4,000 to 5,000 light years away, the light you're seeing from those stars left around the time the ancient Egyptians were building their first dynasties. Even within this local sample, stellar death happens. Stars cycle through their lives. And here's the specific problem. For stars at the far end of that range, you're seeing them as they were 4,000 years ago. If one of them went supernova 3,000 years ago, the explosion has already happened. The light from that explosion is currently traveling toward us. It will arrive in 1,000 years. Tonight, looking at that star, you see it burning normally. You have no idea it's gone. We have no way to know right now which of the stars above us are already dead and which are still burning. This is not hypothetical. Take Betelgeuse, the red supergiant marking Orion's shoulder, about 700 light-years away. It is unmistakably near the end of its life. A star of its type and mass will eventually collapse and explode as a supernova. When it does, it will be briefly visible in daylight from Earth. Now, could that explosion have already happened? Yes, it could have collapsed 600 years ago, and the light from that explosion is still making its way here. You can go outside tonight, find Orion, look at Betelgeuse, and what you're seeing left that star 700 years ago, during the 14th century on Earth. What that star is doing right now is something we simply don't know. It might already be a neutron star. You might be looking at a ghost. Scale that up to the full disk of the Milky Way, that band of diffuse light arcing across the sky and stars thousands of light years away. The chances that every single one of them is still burning in this actual moment are essentially zero. Some fraction have already exploded, some have already collapsed. Some white dwarfs out there used to be stars that we're still receiving light from, because the light from their living days is still in transit, while the star itself has long since dimmed and gone cold. We are receiving transmissions from the dead, and we can't always tell them from the living. Now zoom out further, not just from our moment in history, but from the entire human timescale. The universe is about 13.8 billion years old. Our sun formed 4.6 billion years ago, which means we're sitting at a relatively late point in cosmic history, but not the end. The sun has roughly 5 billion years of fuel remaining. The galaxy has been forming stars for most of its 13.6 billion year history, but the rate has been declining for billions of years. We are past the peak. The Milky Way is not in its early, energetic, star-forming days. It's middle-aged, slowing down, running low on gas in the most literal astronomical sense. Red dwarf stars, the most common type in the galaxy, dim and small, burning hydrogen slowly, have lifespans measured in trillions of years. The universe is only 13.8 billion years old. Not a single red dwarf has ever died of old age, not one. They're all still burning, every red dwarf that ever formed, because the universe hasn't given them enough time to finish. In that sense, we live in the early universe. The era of stars, cosmologists actually call it the stelliferous era, will last for something like 100 trillion years. We are 13.8 billion years into it. We are at roughly the 1/100% mark. But the stelliferous era ends. Every star burns out eventually, even the long-lived red dwarfs. The last star in the Milky Way, some dim red dwarf, invisible to the naked eye, burning quietly in the dark, will exhaust its hydrogen in perhaps 10 trillion years and quietly go out, no explosion, just dimming, and then there will be no new light from stars in our galaxy, only the remnants, drifting. After that, the timescales become genuinely difficult to think about. Stephen Hawking worked out in 1974 that black holes aren't perfectly black. They emit a tiny trickle of thermal radiation through a quantum mechanical process, very slowly losing mass. A black hole with the mass of our sun would take about 2 times 10 to the power of 67 years to completely evaporate through this process. That number, 10 to the 67th, is so much larger than the current age of the universe that putting them on the same scale is essentially meaningless. The universe is 10 to the power of 10 years old. Hawking evaporation of a stellar black hole takes 10 to the 67. The ratio between those two numbers is larger than the number of atoms in the observable universe. The end point, if current physics is right, is a cold, dark, nearly empty universe. No stars, no planets orbiting them, no light to speak of. A thin dispersal of particles at temperatures approaching absolute zero in a space so vast and so empty that meaningful interactions become vanishingly rare. This is what cosmologists call the heat death of the universe, though cold death is more accurate, and the Milky Way is already on that trajectory, already past its peak, already accumulating remnants faster than it creates new stars. The graveyard is filling, and it has been filling for billions of years, and it will keep filling until there is nothing left to bury. Go outside on a clear night, away from city lights. Look at the band of the Milky Way, that diffuse stripe of light arcing across the sky. What you're looking at is the disk of our galaxy, seen edge-on from our position inside it. The light from that band has been traveling toward you for anywhere from a few hundred to tens of thousands of years. Some of those stars exist, some of them don't anymore. You cannot tell which is which. There are roughly 100 million neutron stars in that galaxy. If you could somehow make them visible, they would outnumber the bright stars visible to the naked eye by about 10,000 to 1. The dead outnumber the living by a staggering margin, and the margin grows larger every century. Every bright star visible to the naked eye, Sirius, Vega, Rigel, Antares, Arcturus, every single one of them is more massive than our sun. That's why you can see them. They're brilliant precisely because they're burning fast. And burning fast means dying young. Rigel, the blue supergiant in Orion, has a few million years left at most before it explodes. Antares is a red supergiant so far along in its evolution that it may have already exploded. We don't know. The light hasn't arrived. The night sky, in other words, is not a representative sample of the galaxy. It's a selection biased toward the massive, the short-lived, and the recently formed. The majority of the galaxy's actual stellar population, and the quiet, dim, long-lived red dwarfs, you can't see most of them without a telescope. What you're shown, without asking, is the dramatic and the dying. Here's where I'll be straight with you about what we don't know, because I think that matters. We don't know exactly how many stars are in the Milky Way. The range is 100 to 400 billion. That factor of 4 uncertainty is real and honest. We can't see through the galactic center. The dust is too thick. Dim red dwarfs are hard to census at large distances. We're working from samples and extrapolating carefully. The 100 million neutron star estimate comes from modeling stellar evolution rates over the galaxy's history. It isn't a direct count because most neutron stars are invisible unless they're actively pulsing or pulling material from a companion. And we don't know with precision when Betelgeuse will explode. Estimates range from tens of thousands of years to potentially much sooner. The unusual dimming in 2019 and 2020 turned out to be a surface mass ejection and a resulting dust cloud, not the beginning of collapse, but eventually collapse will come. These aren't failures of physics, they're the current state of measurement. The universe doesn't hand out answers. You have to work for them, and sometimes working for them reveals that the honest answer is, we're not sure yet, here's our best current estimate, and here's how we'd know if we were wrong. Let me put it all together. You live inside a galaxy 100,000 light years across, containing somewhere between 100 and 400 billion stars. That galaxy formed about 13.6 billion years ago and has been converting gas into stars ever since. But the rate has dropped dramatically from its peak. Stars are dying faster than new ones are being born. The galaxy is accumulating remnants, white dwarfs, neutron stars, black holes, that no longer shine and never will again. The fraction of stellar objects in the Milky Way that are dark remnants already numbers in the billions. When you look at the night sky, you're not looking at the galaxy as it is. You're receiving old light, some ancient, some merely old, all of it delayed, none of it current. The stars you see might still exist. Probably most of the nearby ones do. But the more distant ones, the ones that form that band of light we call the Milky Way, some of them are already gone, already collapsed, already cold, and you're seeing their last transmission still in transit, arriving at your eye tonight. The beautiful thing, and I do think it's beautiful, is that we worked this out. From a small planet with telescopes and spectrographs and patient, careful measurement, we determined how stars form, how they burn, how long they last, how they die, and what they leave behind. We did this for objects 26,000 light years away that we will never visit. We will never touch a neutron star. We will never watch a supernova up close. And yet we know, with genuine confidence built on real evidence, what they are and how they work. That is not a small thing. That is one of the more remarkable things our species has ever done. The next time you stand under a clear sky and look at the Milky Way, that ancient light, carrying news from stars, some of which no longer exist, arriving at your eye on an ordinary night, you're not just looking at something beautiful. You're looking at a graveyard and a nursery at the same time, a structure that is both dying and creating, that has been doing this for 13 billion years and will continue in some diminished form for trillions more until the last red dwarf quietly exhausts its hydrogen and the final star in the galaxy goes dark. And then there will be the remnants. Billions of cooling white dwarfs, millions of spinning neutron stars, millions of black holes, all drifting through a dark and expanding universe, growing further apart with every passing billion years, until even they are gone by processes so slow they make stellar death look instantaneous. That's what's above you when you look up, not a ceiling painted with lights, a history, a graveyard, a slowly closing account. And here's the part I keep coming back to. The atoms in your body were forged inside stars that died before our sun existed. The iron in your blood came from a supernova. The calcium in your bones, the oxygen in your lungs, all of it was cooked up inside stellar cores and scattered across space when those stars exploded. You are not separate from this graveyard. You are made of it. The Milky Way didn't just create the conditions for life, it built the raw materials of your body in the hearts of stars that have been dead for billions of years, and you are, in the most literal chemical sense, what a star leaves behind. And the fact that some of that stellar debris arranged itself into something that can look back up at the sky and understand what it's seeing, that's not nothing. That's actually quite something.